All right, so today we're continuing on with Bayesian inference, and we are looking at the beta binomial model, okay? So we're looking at Bayesian inference, and in particular, the beta binomial model. And let's see, this is lecture 2, week 5, Monday. Okay, and all right, so on Friday we were talking about the beta binomial model, and I said we've got this bucket, and when we look at the bucket, you get to see one red M&M go in, one green M&M go in. Then we close our eyes and we hear a whole bunch more M&Ms going in. We don't know what are red and what are green. And then we open our eyes and we're asked what proportion of the bucket is green. Okay, and at that point, we have no idea what proportion in the bucket's green. Any value between 0 and 1 seems equally likely, and so our distribution prior to seeing any data is just a flat uniform distribution from 0 to 1, because these are all the probabilities that the proportion that the bucket, all the proportions of green that could be in the bucket, right? So let me just kind of recap. So Friday, whoa, all right, hang on. I gotta, let's reopen this. Where we were, week 5, Monday. Okay, so Friday's example was we see one red and one green M&M go into the bucket. Okay, close our eyes. We close our eyes. And here, more M&Ms poured in. Okay, and then and before we get to see any observations, okay, you know, we are asked what is the probability of drawing a green M&M? Okay, and so so right now, so prior to seeing any data, any proportion between 0 and 1 are equally likely, because we don't know if it was all red that was being dumped in, or if it was all green that was being dumped in, or a mix. And so all probabilities of green between 0 and 1 are equally likely. So and we said this is a beta 1-1 distribution. Okay? And this is going to be, and we'll say this is, we'll say theta comes from beta, and so theta is going to be the probability of drawing a green from the bucket. So that's the symbol for the parameter we're using, probability of drawing green from the bucket. Okay, so yeah, so right now our prior is theta comes from a beta 1-1 distribution. Sir. Okay, Are there any questions so far? Is this okay? This is all okay. All right, so let's say we observe some data. Let's say we take 5 M&Ms with replacement, and we see 2 green ones and 3 red ones, okay? So we're going to say, let's look at our data, and we will look at 5 M&Ms with replacement, and we see 2 green. So what we observe 2 green, 3 red. Okay. And what we're going to do is we're going to make a we're going to calculate the likelihood of our data for, based on theta. Okay. So just what's the difference between a PDF and a likelihood function? What's that? Yeah, so a likelihood function doesn't need to integrate to 1. A likelihood function is a function of the parameter, a function over the parameter, and the data is fixed. A PDF, it's a function of the data, and the parameters are fixed. Okay? So we're going to make a likelihood function. So the likelihood is a function over the parameter theta. Okay, given some fixed data. Okay, and we're still asking, what is the probability of this fixed data given different values of theta? Okay, this answers the likelihood, answers the question, what is the probability of getting this fixed data for different values of theta? Okay, so if we're dealing with kind of this situation where we're drawing M&Ms with replacement, and we get 2 that are green and 3 that are red, okay, and again theta is the probability of drawing green. What we have in our data is n equals 5 and x equals 2. We're going to ask the probability of our data given theta. Okay, so the data is fixed, and it's a function of theta. So we might just say, what is the probability if theta is equal to 0.5? And this would be, all right, it would be 0.5 squared times 1 minus 0.5 cubed, and we get 0.5 to the 5th. And if we calculate this out, this becomes 0.03125. Okay, but we can, what about for a different value of theta? Okay, so we can say, what is the probability of our data getting this fixed data for different values of theta? We could ask, what is the probability of our data if theta is equal to 0.8? Right? So if the probability of getting green is 0.8, we need to get 2 green, 0.8 times 0.8, and then we need to get 3 red. So that's going to be 1 minus 0.8, or 0.2, and that needs to happen 3 times. Okay. There might be some proportion, some constant here, but this would just be the sequence: green, green, red, red, red. Okay, and that's fine. And I think this ends up being something like 0.00512. 0.2 to the 3 times point. So I think it's actually equal to that, yeah. 0.64. 8 times 64, yeah. 0.00512. Okay? And that makes sense, right? If the probability of drawing green is 50%, we have a greater likelihood of getting 2 green and 3 red. Then if the bucket was mostly green, then it should be a rare circumstance to get only 2 green and 3 red, right? Okay, and we can just kind of rewrite this as a function, and we can just say the likelihood, the probability of getting our data based on different values of theta is going to be equal to theta to the x times 1 minus theta to the n minus x, right? So in this case, this becomes theta to squared times 1 minus theta to the 5 minus 2, or to the third. So we have theta squared times 1 minus theta cubed. Is this okay? All right. So, so what we have here is we've got the likelihood function of our data. Looks like this. It's currently theta squared times 1 minus theta cubed, and this is the probability of our data given some value of theta. Okay. We also have the prior distribution of theta, which is equal to probability of theta. And so this is the prior distribution of theta. So this is the distribution of theta before looking at our data. And we said this is going to be a beta 1, 1, right? And this is equal to 1 for where theta is in the interval 0 to 1, right? Is that okay? Because we said all values between 0 and 1 are equally likely, so then our equation for this prior distribution before looking at any data is just 1. Okay? And so using Bayes' rule, this is what we have. We have the probability of theta given our data. So now we want to know what's the probability of a certain value of theta given our data. This is going to equal the probability of our data given theta, our likelihood, times the probability of theta divided by the probability of data. Okay, that's just what Bayes' rule is. And this is going to produce a PDF, okay? So this will be a PDF for theta. This denominator part, this probability of data, theta does not appear here, okay? This does not depend on theta, okay? And its formal definition, probability of data is equal to the integral of the data given theta times probability of theta. It's basically the numerator over evaluated across all possible values of theta, okay? So it's the integral of the numerator evaluated at all possible values of theta. Okay, but this is, it doesn't matter. All that matters is that because it doesn't depend on theta, this whole thing is just going to be a constant with respect to theta. Right? It's just a proportionality constant. So it doesn't depend on theta. So this integral is like really complicated. It's often a pain in the butt to try to calculate, but we don't have to worry about it. We just say, you know what, this is just going to be a constant, okay? And really, its only purpose is so that if we say we have a function that looks like the numerator, it's so that this thing integrates to 1 so that it qualifies as a PDF, because that's the requirement to be a PDF, is that the whole thing has to integrate to 1. Its sole purpose is so that the numerator will integrate to 1, or not the numerator, so that this function integrates to 1, okay? Its purpose is so that the function, which is a PDF, will integrate to 1. Okay. So what we can say is the probability of theta given our data is proportional to our likelihood, the data given theta, times the probability of theta. Okay, and so in our case, the probability of different values of our parameter theta, the probability, kind of the density for our proportion that's green, given that we saw 5 M&Ms where 2 of them were green, this is going to be proportional to the likelihood, which we have written up here, theta squared times 1 minus theta raised to the third, multiplied by our prior distribution. What's our prior distribution? Our prior distribution is just 1. Okay? For theta in between 0 and 1. Is it okay? Okay, let's just see what this function looks like. Okay, and again, it's proportional to it, so that if we integrate this thing, it's going to integrate to 1, but it's proportional to this thing. All right. So prior to seeing any data, okay. So we've got an online poll going, so choose B, and I'm going to close it in like 1 minute here. Prior to seeing any data, my beliefs about theta is flat and uniform from 0 to 1. And then our prior, I'm sorry, this is what we have. Okay, so this is the prior. Prior looks like that. Okay, and then now that we've seen 5, now we have seen 5 M&Ms, and 2 are green. Okay, so my beliefs about theta, now that I've seen the data, will be this. Okay, it's the probability of theta given our data, and we don't know exactly what it is, but we know it is proportional to theta squared times 1 minus theta cubed. Okay, and so we can use R to kind of just see what this looks like, and because it's unidimensional, I'm going to go ahead and just do grid approximation. Okay, so because it's easy, right? So we'll do it's a unidimensional function. We will use grid approximation. All right, and so when I go to R, okay, so I'm going to just make a simple sequence, and we'll go from 0 to 1, and we'll do by equals 0.01, all right? And then kind of my posterior function will be a function of theta, and the value it's going to return is going to be theta squared times parentheses 1 minus theta to the third. Okay, and then what I'm going to do is I'm going to plot S versus the posterior of S. Okay, and that's what it looks like here. Let me just do PCH equals 19 and CEX equals 0.5. Okay, that is our grid approximation. Okay, so I've calculated this at basically 100 different values of theta, and we said what's the likelihood of our data? Okay, or, I mean, what's our posterior distribution, which is 1 times the likelihood here, and we're used to seeing a smooth thing. We do type equals L, but don't be confused. I mean, don't be misled. When you do type equals L, all it's doing is it's just connecting lines to those 100 dots. Okay, all it is this, but we just drew a line to connect all the dots, so it looks like a smooth thing. But because it's a computer, the computer doesn't understand math. It doesn't know that continuous numbers exist. It can only represent a finite number of numbers, and so it's actually a grid approximation. Although this looks like a smooth curve, it's not. It's really just this where the dots have been connected. So this is, grid approximation. That's fine, okay? And, because the computer is so fast, we can ask for, 1,000 points or, 10 million points, and they'll be so close that it looks like, for all intents and purposes, it looks smooth. But computers don't know how to graph continuous functions. That's not the realm of feasibility. Okay, I'm going to go ahead and close our poll. Okay, so this is our updated belief about theta now, okay? So let's say I go and we're going to draw more data, okay? So right now, let's say my beliefs about theta is that the probability of theta is proportional to theta squared times 1 minus theta to the third. And we've got this little picture here to say this is what it looks like. Okay, so this is what I believe about theta right now. Okay, and then I'm going to draw more data. All right. So you might ask, why is it just probability of theta and not probability of theta given data? Because that's what we had on the previous slide. Okay, this represents like a new day. Okay, and we're like excited to draw more M&Ms out of the bucket, and now we say, okay, because I saw stuff yesterday, these are my beliefs about theta today. Okay, so we've updated our beliefs, and these are our beliefs about theta. We're not, and we're just kind of taking into experience what we have in the past. So this is prior to seeing new data, prior to seeing today's data. This is my beliefs about theta. Okay, so right now my beliefs about theta, we can think of this as my beliefs about theta prior to seeing today's data. And thus, these beliefs do not depend on today's data. Okay? Prior to seeing today's data, they don't depend on. Okay, so we're going to draw more data, all right, and we're going to say we get 5 more M&Ms with replacement. Okay, and this time I get 1 green and 4 red. 1 green and 4 red, right? And so what we want to find is, we want to say, what is the probability of theta given our data, right? And using Bayes' rule, we know that this is going to be proportional to the data given theta times the probability of theta. Okay, so this represents our updated beliefs about theta after seeing data. So this is updated beliefs about theta after seeing the data. All right, and then this is the likelihood of our data for a given theta. And this is my beliefs about theta prior to seeing today's data. Prior to seeing the data, okay? That's what we have, okay? And so, okay, so my prior beliefs, this part is what we have here, okay? So prior to seeing today's data, this is what I believed to be true about theta, okay? I said it's proportional to this function here. So we got theta squared times 1 minus theta to the third, okay? And then the likelihood of our data, what is this, okay? We've seen 1 green and 4 red. So what is the probability of getting 1 green? That's going to be theta raised to the 1. And what's the probability of getting 4 red? That's going to be times 1 minus theta raised to the 4. Okay? And so I multiply these two together. And what am I going to get? I'm going to get theta to the 3 times 1 minus theta to the 7. Is that okay? So I got theta to the 3 times 1 minus theta to the 7. All right, so let's just go ahead and take a look at what that graph looks like. Okay, and again, we'll do grid approximation. So I'm going to redefine our posterior function to be theta to the 3rd times 1 minus theta to the 7, okay? And then let's go ahead and just plot this. Okay, so this is what we have, okay? So before we said 40% is kind of the most likely value, but sure, it could be 20%, it could be 60%, it might even be 80%, okay? Because we had seen, so far we had seen only 2 green and 3 red. It could be 80% green. It would be unlikely. I mean, it's not super probable, but it could happen where you get 2 green and 3 red, okay? But then after seeing 5 more data points where only 1 of them was green, we update our beliefs and everything kind of shifts over a little bit and gets a little bit more defined around here. And now our most likely belief is around 0.3, okay? And we can see, having a proportion of 0.8 seems very unlikely. And, values between 0.2 and 0.5 are kind of like, these are the likely values here, okay? So this is basically, at this point, we have seen a total of 10 data points, 10 M&Ms, where 3 of them are green. Here, maybe I'll fit it right there. Okay, where 3 of them are green and 7 are 7 are red. Okay, so so let's see. So our resulting distribution, okay, so after more data, okay, our resulting distribution, this is our posterior, is the probability of theta given our data is proportional to theta raised to the third times 1 minus theta raised to the 7. Okay? Now, if we want to turn this into a PDF, we need to find some constant so that the thing integrates to 1, right? So we, if we want it to be a PDF, we need to find a constant so that the integral of the constant times theta to the third 1 minus theta to the 7 over d theta will equal 1. Okay, and what we see is that this thing is in the form of a beta distribution. Okay, so if we recall what a beta PDF looks like, a beta PDF, if we go to Wikipedia, beta distribution, our beta distribution, they use x, but it's theta to the alpha minus 1 times 1 minus theta to the beta minus 1 divided by beta function of alpha comma beta. Okay, so this is theta to the alpha minus 1 times 1 minus theta to the beta minus 1 divided by the beta function of alpha comma beta, right? So what this is, we have theta 3, theta 1 minus theta 7. This is going to be theta to the 4 minus 1 times 1 minus theta to the 8 minus 1. And then we've got beta 4 comma 8, all right? And so this becomes theta to the third 1 minus theta to the 7 divided by the beta function of 4 comma 8. This is just some constant so that the numerator integrates to 1. That's its only purpose. Okay. And this can be defined as the beta 4-8 distribution. Okay. So just kind of recapping what we had, we started off, our original prior was beta 1 comma 1. Then we observed data n equal to 5 and x equal to 2. And what happened is we update to beta 3 comma 4. And then we observe more data, and this time n equals 5 and x equals 1, and we update and we get beta 4 comma 8. So at each step, when we observe more data, we update our distribution, and we get something like this. This works because the beta binomial is this nice friendship, and it's called the conjugate prior, because when you observe data from the binomial, if you've got basically a binomial thing generating your data, and you're trying to update your beliefs about theta, when we combine the likelihood and the prior, they're in the same form. They multiply nicely, right? They multiplied nicely. We were able to do theta times whatever, and we get this nice thing. And the idea is basically, I just want to use the same values, same letters that appear in our textbook. So I kind of did this loose, broad overview thing, and definitely you have to read chapter 6 for a slightly more rigorous, the more rigorous math here. But basically, if your prior has distribution beta A comma B, so these are the letters that, this is the letters that our textbook uses, okay? And then your data has N trials and Z successes, okay? The posterior will have distribution beta A plus Z, comma, what is it? N minus Z plus B. Okay. Or maybe, you know, we can read, basically it's kind of your prior heads is kind of like the data you've seen prior, right? So this is kind of like the, you know, the prior heads or the prior green plus data green in our case. And this is over here, it's kind of, I should probably put it in the same order here. And this is the prior red plus the data red, okay? So it ends up being, you know, prior to seeing it, you had seen one red and one green go into the bucket. And then after 10 M&Ms being drawn, we had seen 3 more green and 7 more red. And so we end up getting 1 plus 3 in the front, 4. And then for the, in the second shape parameter is 1 plus 7, 8. Okay? So if we, our prior was beta 1, 1, okay? And then we saw, you know, 2 sets of 5 data points, 2 sets of 5 M&Ms with a total of 3 green and 7 red. And so this ends up being, at the end of the day, we get beta 4 comma 8. We just add 3 to the one of them and 7 to the other. Okay. Yes. 2 sets of 5 M&Ms. Or I'm just going on with our M&M bucket example, if that's all right. Okay. And again, make sure you do your reading. It does a little bit more math, okay, than kind of what I'm here. Here I'm just kind of using a little bit more intuition, an intuition-based approach, and they do a little, just a teeny bit more math here, okay? This is still very intuitive thing, okay. So this was starting off with a flat prior, and I just want to kind of give an example where, you know, so when we started off, we said, you know, what proportions in the bucket? We said the bucket could be anything between 0% and 100% green, okay? Sometimes that's not often the case, all right? And so I want to do an example where maybe our prior is not that, okay? And I'll link this. Let me find this. Okay, so we got baseball. What is this? Beta distribution for baseball. Is this the one we want? Yeah, here we go. Okay, so we're using 81-219. Okay, so in baseball, some of you follow baseball, some of you don't, and it doesn't matter, okay? There's something called a batting average, okay? All right, and what is a batting average? The batting average is a measure of how often a batter gets to base. Okay, because in baseball you want to hit the ball and run to base, and if you safely make it to a base, you get a base hit. Okay, so batting average is basically number of base hits, okay, which is batter safely reaches base, divided by number of plate appearances. Which is basically opportunities that the batter has. Okay, and it's hard getting to base. Okay, the pitchers are really good. They throw really fast balls, and when you hit it, so it's hard to hit the ball. And if you manage to hit the ball, the fielding is often pretty good, and it's hard to get to base. All right, and so if you get to base 30% of the time consistently, you are considered a great baseball player. Okay, the highest batting average of all time, highest career batting average. Let's see. Okay, the highest career batting average of all time is Ty Cobb with a batting average of 36.6%. Okay, 0.366. This is the highest batting average of all time. And then if you get on base 32% of the time, you are in the top 50. Okay, you are top 50 of all time in the history of baseball. Okay, so 32% will get you into the top 50, and 31% will get you into the top 100 all-time baseball. Okay, this is like there's not a whole lot of people over 30%. Okay, and then I don't know. Is there an article for lowest career batting average? Let's see. Oh, there is. Look at this. Okay, John Lester and the worst hitters of all time. All right. This is I don't know. Okay, I don't want to. Usually, on the low end, if you're under like 20%, you are considered terrible. Okay, so there's like if you're an MLB, if you are a professional baseball player, we can say likely your batting average is somewhere between 20 and 30%. Okay, because if you're much lower than that, they're not going to hire you. And that as a batter, right? Pitchers are different, but. Okay, and so we can kind of make a beta distribution reflecting this. We can say, prior to knowing anything about a baseball player, if we said, what do you think is this player's baseball average or batting average? Okay, so you say, here's a brand new player coming who wants to join Major League Baseball, and we say, we don't know anything about him, but we think he's Major League caliber. Okay, so your guess for batting average is going to be somewhere between like 20 and 30%, and we reflect this in our kind of our prior distribution. Okay, and here's the thing. Let's say you see like you're scouting the player, and you see the player, or maybe it's the beginning of the season. The player goes up to bat 10 times and gets 5 base hits. Okay, so let me just kind of do this. So prior to data, okay, we get a distribution that's like somewhere between 0.2 and 0.3. This is what it looks like, right? Something like that, right? This might be just kind of borrowing the numbers, 81 to 19. Okay. And then we see some data, and n is equal to 10, and we get z is equal to 5. Okay, so our data has a batting average of 50%. Okay, are you then going to say, oh, this person now is the greatest baseball player of all time because his batting average is 50%. No, we would just say, wow, he had a good series, like he got lucky, you know, had some good lucky plate appearances, right? Whereas if over the course of many plate appearances, like n is equal to 300 and z is equal to 100, so we have now an average of around 0.33, this is now strong evidence of a very strong player, okay? Now we have lots of evidence, or more evidence, for a strong player, versus over here, this could be, you know, a fluke, okay? And if we update our posterior distribution using this versus this, what we would find is that this will still produce a band that looks almost identical to this, whereas updating it with this data will produce a more narrow band, indicating greater confidence in the result, okay? So we would end up getting something that looks still kind of like this, whereas over here we would get something that looks more narrow, indicating more confidence in our values, our beliefs about the player's true batting average, okay? All right, we'll end here for today. We'll see you guys on Wednesday.